the armature reaction. So in this class, we'll look into the generator characteristics. So first of all, we'll talk about the shunt generator. Shunt generator. So the first type of characteristics, generator characteristics, is a no load characteristics. So they are also called as an open circuit characteristics, OCC. So for obtaining these open circuit characteristics, generally the machine is operated as a separately excited machine. So this is how a shunt machine would look like. So we'll be having a field winding. This is the armature, and we have our load. Okay. So this is the field winding, RSH. Okay, this is our shunt generator. But to obtain the open circuit characteristics, we have to operate the shunt generator as a separately excited generator, which means the field winding is excited from a other source, from another source. Like, so this is our field winding. This is the external supply. This is a rheostat. Then we have our armature here. Then we have the load. So since it is an open circuit characteristics, so we don't consider the load in this case. Okay. So what are the conditions to for a machine? And yeah, open circuit characteristics are drawn between the terminal voltage across the armature and the field current IF. So the field winding IF. So if you see here, initially when the field current is zero, there is some residual voltage. This is because even though the field current is zero, there will be some residual flux produced by this field winding. So because of which there will be some induced EMF in the armature and the machine rotates. That voltage we call as a residual voltage. So after that, when you keep on increasing the field current, the flux will increase. We know that E is equal to pi Zn by 60 into T by A, right? So E is proportional to phi. So as field current, which is proportional to field current. So as field current is increasing, the flux increases, the induced EMF increases. So the voltage keep on increases. At some point, even if you increase the field current, flux gets saturated. So the voltage reaches its maximum value, that is the rated value. So for this entire process to work, there are some conditions to be satisfied, which are called conditions for satisfactory self-excitation. So the first condition is there should be some residual flux present in the poles of the DC machine. First thing. Next, the field resistance. This field winding has some resistance called RSH or RF. This field resistance should be less than the critical resistance value. And the next point, this is the second point. Third point is the speed. The speed at which the armature is rotated should be greater than the critical speed NC. Fourth point is the field winding should be properly connected across the armature winding. Why? Because suppose if the field winding is connected in reverse to the across these terminals, the current, the flux produced by the current flowing through this winding will cancel the existing residual flux, due to which there won't be any buildup of voltage. So the field winding has to be connected properly across the armature windings. That is the fixed. There must be some saturation in the excitation of saturation. higher. There should be some residual voltage. After that, as we take it, this is a no load character. Next one is the load characteristic. We'll talk about external characteristics is a discuss internal characteristics is a plot the armature current or separately excited machine. So we have armature excited by an external supply. It is connected to the so this is the internal characteristics, the plot between edge across armature to this armature current IA. So as you keep on increasing armature current, say the initial voltage is EG. To increase the armature current, what happens is the armature reaction increases because of armature reaction increases because armature reaction depends upon the load. As we increase the armature current, the armature reaction effect increases, which means the armature flux increases, which will oppose the main field flux as the net flux will decrease, because of which the induced voltage will decrease as well as terminal voltage E also decrease. So this is the internal characteristics. Now the external characteristics means that is nothing but the terminal voltage. It is a drawn between terminal voltage and the armature resistance. So when we look at the terminal voltage, we have to consider armature resistance drop also, RA, IA, RA drop also. So in addition to the armature reaction drop further. So this drop is due to armature reaction, drop is due to the armature resistance drop. There is one more, voltage regulation. Percentage voltage regulation is given by the formula by induced voltage is a terminal voltage. So voltage regulation is a change in voltage from no load to full load expressed in terms of full load voltage. So an ideal generator should have zero voltage regulation. Is it clear? Slide. Same what I have discussed earlier. So, next, where we will be talking about shunt generator load characteristics. Speed and armature field current IF is given by RSA. Characteristic. First one is an internal character. The plot between induced EMF E the induced voltage at speed without load. So as we connect the load, the armature current flows, because of which the armature flux exists and the armature reaction happens, so which will oppose the main field flux. So as the armature current increases, the armature reaction increases and the opposition increases, decrease, and the voltage keep on dropping. So this drop is due to the armature reaction. Next one is external characteristics. That is plotted with respect to the terminal voltage. So which means we have to include one more drop, that is armature resistance drop. But the drop will be more resistance drop. Clear, Rachna? Let me know. Okay. Slide I'll talk about the series generator characteristics. Generally, series generator should not self-excitation possible in series generator. A minimum load has to be connected. Is when there will be a closed path for the field current to flow. Okay, when the current flows, then only the flux will produce, and then the induced EMF starts happening, increasing the field current. See the series. So here we have to connect. If there is no load, it's open circuit, so there won't be any current flow. Self-excitation possible. Respect to the voltage due to the residual flux in the poles.
Sir, can you be a bit louder, sir? Also, voice has some.
So initially there is some residual voltage to the residual flux in the poles. So after that, as keep on increasing the load, what happens is current flowing through the field winding increases, due to which the flux produced by the field winding increases, and the voltage starts building. And again, when it will reach a point where the flux gets saturated, means even if you increase the current, the flux won't increase any further. Corresponding voltage we call it as a rated voltage. So this is the open circuit characteristics. Next is the load characteristics. And the first one of load characteristics we have is the internal characteristics. Internal load characteristics. Other one is the external load characteristics. First we'll see the internal load characteristics. similar to the OCC, but only difference is there will be an RH reactions drop has to be considered. It looks same, but there is some drop. This drop is due to the armature reaction drop. Next one is external load characteristics. The plot also looks similar to the OCC, but we have to include one more additional drop, that is armature resistance drop, that is IA RA drop. So this is external load characteristics, and curve in middle is the internal load characteristics. Okay. Sorry, clear, Rachna? If you have any doubt, let me know. Okay, I hope it's clear. Then I'm going to the next slide. So this is what I have covered in the earlier slide. To make the self-excitation possible in series generator, a minimum has to be connected. So then the closed path will be formed. In series generator, terminal voltage increases as the load increases because proportional. And this characteristic is called as a voltage rising characteristics. And for series generator, voltage regulation is negative because earlier we have seen the formula for voltage regulation, E minus V by V. So as the load increases, what is happening? The V is increasing, because of which voltage regulation becomes negative. Next slide will talk about compound generators. Compound generators are similar to the shunt generators, but there will be a few extra series field turns to make the terminal voltage almost constant. So there are two types of compound generator. One is a differentially compound generator, other one is cumulatively compound generator. Differentially compound generator is one in which the series flux will oppose the shunt field flux, whereas in cumulatively compound, both will get aid each other. So if you draw generally compound generators, so the expression for voltage can be given as V is equal to induced EMF E minus armature resistance drop minus series field winding resistance minus brush drop. So if you see here the plot, it's drawn between V and the load current. So the level excited means the voltage drop is almost zero. Even though you increase the current, the load current, the voltage remains almost constant. So over excited is one where the voltage keep on increasing if the load current gets increasing. Under excited is voltage decreases if the load current is increasing. In case of a differential compound, what happens is beyond some point, even though increase the load current, the voltage keep on decreasing. So if give you the condition, so if we equal, suppose if voltage is zero, this voltage is zero, then E is equal to IARA minus this drop, right? Which means the voltage is almost constant. So that is called as level compound generator. If E equal to IARA plus ISC RSC plus brush drop. And if E is greater than IARA plus ISC RSC plus brush drop, we will is a positive. So this is called over compound, over excited or over compound generator. And similarly, if E is less than IARA plus ISC RSC plus brush drop, V becomes negative if we keep on increasing the current. So that is called as an underexcited machine. So in differentially compound generator, that is the last curve you see here. Last curve, this one. Terminal voltage drastically reduces as the load current is increasing. So generally these type of generators are used for arc welding. Okay. Is it clear? No? Let me know if you have any doubt. Okay, we'll see some problems here. So this is a previous year gate question. So a DC shunt generator, which is operating in saturation region, gives no load terminal voltage of 200 volts. What will be the voltage if speed is increased by 10%? So, operating in the saturation region means the flux is constant. Increase the current, the flux won't change. So we know that E is equal to phi Zn by C by A. C is proportional to phi n. That is the number of conductors. P is the number of poles. A is the number of parallel paths, which are all constant. So E proportional to phi into n. But in the question they have specified the flux is constant, which means it's proportional to n. 1 by E2 equal to n n2. What they have specified, what will be the voltage if speed increases by 10%? Speed increases by 10% means n2 equal to 0.1 times n1 by E2 equal to 1 by n2, which is 1.1 cancel, and E2 equal to 1.1 times E1. So what will happen to the voltage? So the voltage also increases by 10%. Yeah, I hope this is clear for the next. So the next topic is DC generator losses. So the basic classification of DC generator losses is, let's say, total losses. DC machine can be classified into three types. One is a copper loss. The other one is the iron loss, mechanical loss. These copper losses are further classified into armature copper loss, due to the armature winding, have the shunt copper loss due to the shunt winding, have series copper loss due to the series field winding. Iron losses are classified into series losses and eddy current losses. Mechanical losses are classified into friction and windage losses. Let's talk about iron losses. Losses which are further classified into eddy current loss and hysteresis loss. Eddy current loss. Eddy current losses are produced due to the flow of currents through the armature. So, whenever the currents flow through an armature, armature provides a closed path for these currents. So, whenever there is a closed path, so the current flowing through the armature will create heat in the armature, because of which some energy is lost in the form of heat. This is called as an eddy current losses. To avoid this eddy current losses, what generally do in the machines is the armature has to be laminated. So instead of making the armature with a single solid material, it is made up of a number of laminations. One is the hysteresis loss. Hysteresis losses are due to the magnetic reversal of the armature core. So the hysteresis loss for a given material is given by the BH curve. Generally, we know the BH curve looks. So this area under this curve gives the hysteresis loss. So to reduce the hysteresis loss, the area of this curve has to be less. So we have to select a material, appropriate magnetic material, which has a less BH curve. Okay. These magnetic losses, iron losses are also called as a magnetic losses. So these magnetic losses and mechanical losses combinedly called as a stray losses. We can also call them as a constant losses because they don't vary much by varying the load. Okay. Whereas the copper losses, these are called as a variable losses because they depend on the load current. So as the load current varies, the current flowing through the field winding and the armature winding gets varied. So thereby the loss is varies. Now are you clear with the classification? Let me know if you have any doubt. Okay, we'll go to the next slide. So this is what we have discussed in the earlier slide. Here I am showing a better picture. Here we have the classification, and this is the BH curve, how it looks. See, so if the armature is not laminated, there is a closed path for the currents to flow. So because of which eddy current losses will increase. To avoid this, generally, you see here, there are armature is made up of lot of laminations, because of which the eddy current losses can be reduced. So the next one is DC generator efficiency. So generator is one which converts the mechanical power input to electrical power output. Right? So we have a mechanical power input by means of a steam turbine or something. We'll rotate the shaft of the DC generator. So we have mechanical input. And if we subtract iron and frictional losses, that's nothing but the mechanical losses, will give us the electrical power developed in the armature. That is EG, induced voltage, into armature current IA. Then if we subtract copper losses from the electrical power developed, we'll be getting the electrical power output, that is terminal voltage V into terminal current I, VI. So the efficiency is generally defined by output by input. So here the generator output equal to V into I, the generator input equal to output plus losses, right? That is VI plus losses, that is copper losses, that is IA square RA, plus this iron and friction losses also called as constant losses WC, is WC. So the efficiency equal to output by input, that is VI by I plus A square RA plus WC. And this efficiency will be maximum eta max when variable losses equal to constant losses. So what are the variable losses? Copper losses. If these copper losses are equal to our constant losses, then the efficiency will be maximum. Okay, hope this is clear. We'll go to the next slide. So this is what we have discussed. And here we have a better picture. So if they add mechanical input, you will so if you subtract the iron and frictional losses, which are nothing but the constant losses, we will be getting the electrical power developed in the armature. And then if we subtract the copper losses, we will be getting the output power. The generator efficiency is maximum when variable losses are equal to constant losses. So this is one previous year gate question based on the generator efficiency. So what does the question says? A DC generator delivers 45 amps at a terminal voltage of 220 volts. The armature and the shunt field resistance are 0.01 ohms, 44 ohms respectively. They have given us the stray losses as 375 watts. They're asking us to find out the percentage efficiency of the DC generator. Try to solve this. First of all, let's draw the shunt generator. Armature resistance, the shunt field winding. Here we have the so initially it is delivering 45 amps. A terminal voltage of 220 volts. So here we can calculate the field current IF equal to terminal voltage 220 by the field resistance. Field resistance is 44 ohms. This gives us 5 amps. 5 plus 45, the armature current is 50 amps. The total copper losses can be given by IA square RA field copper losses also. So IF square into R field. IA square is armature current is 50 square. The armature resistance is 0.01 plus the field current is 5 amps. 5 square into field resistance is 4 ohms. Around 1125. These are the variable losses. Given us the stray load losses as 375 watts. This is a constant load. So the efficiency equal to output by input into 100. Output is given by V into I. So that is 220 volts into 45. Is 9900 watts. So this is the output. So input equal to output plus losses. 00 plus 1125 plus 375. 0 0 plus 1500 gives you 86%. Try to solve the question once again. Just go through the problem from start to the end, then we'll go to the next. Okay, we'll go to the next question. A DC generator having a combined armature and field resistance of 0.4 ohms is running at 1000 RPM and delivering 5.5 kilowatt at terminal voltage of 110 volts. The speed is raised to 1500 RPM and load is adjusted to 10 kilowatt. They're asking us to find out the new current and the terminal voltage. Assuming the machine is working on straight line portion of the magnetic characteristics, which means the magnetic characteristics are linear. They have given us the P out, that is output power equal to 8.5 kilowatt at a terminal voltage of 110 volts. Then the terminal current, load current can be given as current equal to 8.5 kilowatt by 10 volts, 3 amps. How does our series generator look? Series field winding. Here we have the terminal voltage where we connect the load. The load current, which we have calculated to be as 50 amps. The induced voltage EG or E can be given as V plus A R. 10 volts. Armature current is nothing but the load current. So armature resistance is 0.4. 10 volts plus 130. What they have following. The speed is raised to 1500 RPM and load adjusted to 10 kilowatt. Find the new current and the terminal voltage. So that E is proportional to phi into N and phi is proportional to the load current. I can write E1 by E2 equal to I1 by I2 into N1 by N. So we know E1 is 130, E2 we don't know. I1 is 15, 2 we don't know. N1 is 1000 RPM, N2 is 1500 RPM. This is one expression. Let's keep it like this. We can also write E2 equal to terminal voltage V2 because the speed is changed, so voltage will also change, plus I2 into armature resistance plus series field resistance. Here he is saying that the load is adjusted to 10 kilowatt in the second case. So the output power is 10 kilowatt. Then I can write V2 equal to 10 kilowatt by I2, right? V2 can be written as equal to 10 into 10 cube by I2 plus I2 into RA plus RSC. That is, yeah, they have given that the combined resistance is 0.4. RA plus RSC is 0. See here we have two expressions, right? Two equations. This is equation 2, this is equation 1, which are functions of consist of variables E2 and I2. So if you solve these two equations, you'll be getting current I2 equal to around 53 amps we'll be getting. This is a new current and the new terminal voltage V2 equal to 1 kilowatt by I2. So that is 1870. Okay, I hope the question is clear. What we have done is first initially we have calculated the induced voltage for a given load current. Okay, later they have set the speed as well as the load is changed. So we have derived an expression consisting of variables E2 and I2. So we have derived two equations. All the two equations we got the new current I2. From I2 we have calculated the V2. Okay, we'll go to the next slide. So the next topic is DC generator voltage regulation and some of the example applications of the DC generators. The voltage regulation. Voltage regulation of a DC generator is a change in voltage and the load is reduced from rated value to the low, so which is expressed as a percentage. So the voltage regulation percentage is voltage regulation given by V minus V by V is this voltage, this is the terminal voltage to 100. The example question. To find the voltage regulation of a generator where the rated voltage equal to 220 volts and voltage equal to 240 volts. Find the percentage voltage regulation. So, so the induced voltage EG is the no load voltage, that is 240 minus rated voltage is 220 by 220 into, that is 1 by 11 into 100. That comes around 9.1 percentage. So we'll see some of the applications of DC generators. First one, shunt generators. Shunt generators are used in battery charging and lighting applications. Charging, lighting application. Series generators are used for voltage boosting application in distribution systems. One is the compound generator. We have two types, cumulatively compound and differentially compound. Cumulating compound is used for motor driving applications, whereas differentially compound is used for arc welding. Okay, I hope everything is clear in this slide. What we have discussed. Go to the next topic, that is DC motor. So first we'll start with the basics of DC motor. Motor basics. Generally, there is no constructional difference between DC or generator. Both are same constructionally. DC motor works on the principle that whenever a current carrying conductor is placed in a magnetic field, it will experience a force. This is given by BIL, where B is a magnetic flux density, I is the current flowing through the conductor, L is the length of the conductor. And the direction of force, and this expression gives us the magnitude of force. The direction the conductor experiences the force is given by Fleming's rule. So earlier we have seen in DC generator we have a commutator, right, which converts the AC into DC. The commutator is also called as a split rings. So in DC motor, the commutator helps in producing an unidirectional torque. Commutator helps in producing by making the armature flux stationary even though the armature rotates. So whenever general DC motor will give supply to the field winding as well as the armature winding. So the armature winding is carrying current and it is placed in the magnetic field, so it starts rotating. So once it starts rotating, there will be an EMF induced in the armature called as a back EMF. Next point is, so when the machine operation is changed from to generator to motor across the same supply, the direction of rotation remains the same in case of separately shunt and compound generator, whereas in case of series machine it gets rotate in the opposite direction because that we'll be getting from the torque expression. So we'll see it in the why it is that, and we'll see in the next. Yeah, I hope everything is clear in this. Go to the next. These are the same points which I have discussed. So there is no constructional difference. The direction of magnitude of force experienced by a conductor placed in magnetic field is given by DIL, and the direction is given by Fleming's left-hand rule. The function of the commutator in motor is to create a unidirectional torque, whereas in generator is to convert the AC into DC. Right here, this is a figure showing the operation of a DC. So this is a magnetic field. Magnetic field is going in this direction. This is the conductor. This is the armature. Let's say single coil. Let's say our armature has only one single coil, and this is connected to the supply. So the current is flowing in this direction. So whenever the current flows, according to the Fleming's left-hand rule, the conductor will experience a force in the upward direction. This part of the conductor and this part will experience the downward. And likewise, the coil keeps on rotating continuously. We go to the next. Talk about the mechanical power developed in a DC motor, and we'll derive an expression for the torque. Just consider the field winding here. Connected to the supply, DC coupler, armature current IA, field resistance RSH. It is rotating in this direction, and the back EMF is E. Generally, the mechanical power developed is given by is given PM equal to 2 pi NT by 60. T is the torque produced, N is the speed in RPM. We know that. I can write the terminal voltage V equal to back EMF EB minus IARA. Sorry, it is EB plus, because the terminal voltage is greater than the back EMF. So multiply by current on both sides. I can write I equal to E into IA plus I take the copper loss on the other side. IA square RA gives us V into I. So this is the power input, right? Electrical power minus copper losses gives us the mechanical power developed. That is PM. So I can write 2 pi NT by 60 equal to V into torque developed equal to EIA C by 2 pi N. So we know that EB equal to ZN by C E by A. if I substitute EB here, we have torque equal to E by A by 2 pi n. Still, add pi P by A are constants, is a constant, so I can write torque is proportional to flux into Ia. Generally in a machine, there are two torques. One is the TA, armature torque. This T is nothing but the TA, armature torque, developed by the motor. Other one is the load torque. If armature torque is greater than the load torque, then speed of the machine will increase. The armature torque is less than load torque, the speed decreases. So in DC generator, we talk about voltage regulation, whereas in DC motor, we talk about speed regulation. Okay, I hope this derivation is clear. We'll see some example question. So this is what I have covered in the earlier slide. Year 2014 2 marks question. A 250 volts DC shunt machine has an armature circuit resistance of 0.6 ohms and field circuit resistance of 125 ohms. The machine is operated as a generator and then as a motor separator. So initially the machine is running as a generator. Now it is started as a motor. So the line current of machine in both cases is 50 amps. They're asking us to find out the ratio of the speed as a generator to the speed as a motor. Right, solve this question. So this is the question. We have the field winding, then we have the armature. So they have given us the field resistance is 125 ohms. The armature resistance is 0.6 ohms. So machine is operated as a generator initially. The current is flowing out to a load. Given the terminal voltage is 250 volts. So the line current of the machine in both the cases is 50 amps. Means this current is 50 amps. The voltage is 250 volts. So the field current will be 250 by 125. That is 2 amps. And the armature current is summation of these two. That is 52 amps. The induced EMF E can be given as 250 volts plus 52 armature current into armature resistance 0.6 ohms. This gives us 281.2 ohms. Let's say we call it as E generator. We are operating the same machine as a motor across the same supply. now the same. So now the current goes in. So 50 amps is going in. This is 30 volts. So field is taking 2 amps. So 50 minus 2, 48 amps is taken by the armature. Now E motor can be written as terminal voltage 250 minus current 48 amps into armature resistance 0.6. That is 221. We know that the induced EMF can be given as E is equal to 5Z and 560 into E by A. So E is proportional to M. Flux is constant. Say it's a shunt machine. We're operating the same machine. So E1 by E2 equal to N by N2. They're asking the ratio of speed as a generator to the speed as a motor. Means N generator by N motor equal to E generator by E motor. That is 281 by 221. This comes around equal to 1.27. We'll go to the next question. Question is a gate 2006. It's a 2-mark question. A 220 volts DC machine, 20 amps at 200 volts as a generator. The armature resistance is 0.2 ohms. The machine is now operated as a motor at the same terminal voltage and current. Flux increased by 10%. They are asking us to find out the ratio of motor speed to the generator speed. The same as the earlier question, but earlier there is no change in the flux, but here they have specified that the flux is increased by 10%.
generator operation. The generator is equal V is the terminal voltage, that is plus armature current given as 20 amps. The armature resistance is 0.2 ohms plus 4. We have motor operation. Motor can be V is equal to V minus. So V is 200 volts. Same current flows 0.6. That is equal to 5Z and 5 into by A proportional to 5 into N. But earlier we have considered 5 as a constant, but now in this question the actual flux is increased by 10%. 1 by 2 by N2. 1 by E2 is E1. Let's say what they're asking, ratio of motor speed to generator speed by G equal to by G into 5G by 196. G is 204. Flux is increased by 10%. So 5G. 5G, let's say 5G equal to 5, then 5M increased by 10%. So it will be 1.1 times 5. 5 by 1.15. So 5, right? NM by G equal to 0.87. For the next topic, that is DC motor speed control. So how can we control the speed of a DC motor? For a DC motor, the induced back EMF can be given as E is equal to terminal voltage minus IR drop, right? At the same time, I can also write EB is equal to 5Z and A into P by EB is equal to 5N ZP by 6PA, right? This is, let's say it is a constant for a given mesh. So B is equal to K5N. So this is equation 1. From 1 and 2 I can write IARA K5N equal to V K into 5. K is a constant. I can write N proportional to V minus IRA by 5. So if you see here, by increasing the flux, the speed can be reduced. By decreasing the flux,
speed can be increased. By increasing the armature resistance, IR drop increases for a given terminal voltage and decreases. So there are two types of speed control. One is the field control method, where we are going to vary the flux. Next one is the armature control method, where we are going to vary the armature resistance. In field control method, so let's say we have our shunt motor. What they will do is they will place an additional resistance in series to the field winding. This is the additional resistance which is placed in series with the field winding RSH. So this is our motor. This is connected across the terminal voltage V. So by controlling the value of this R, by controlling the value of this tap position, the current flowing through the field current IF can be varied. So because of which the flux varies. So if I draw the characteristics, see. So this is the field current ISH. This is the speed. Let's say this is the rated speed, unrated. Now if we reduce the field current, what happens? The speed increases. When the flux decreases, speed increases. So it will increase key like this. So in this method, we can get speeds above the rated speed. Go through the derivation, go to the next. Go to the next series motor speed control. This is what we have discussed in the earlier. We will talk about the series motor. Series motor speed control. The first method is field diverter method. And what they will do is our armature. It's the series field winding. They will connect a diverter resistance parallel to the field winding. So this is series field winding RSC. This is the diverter resistance RD. If I write the expression for current, say this is armature current. Current flowing through the field winding is ISC. By using the voltage divider rule, I can write ISC equal to IA into
RD by RD plus RSC. So by changing the value of RD, I can control the value of ISC. So when ISC varies, the flux will vary. When flux will vary, speed will vary. So the flux is proportional to ISC, which is equal to IA into RD by RD plus RS. And the next method is the tapped field method. Tapped field method. In this method, field winding will be has a lot of tabs like 1, 2, 3. So by selecting this tab position 1, 2, 3, 4, by selecting this tab position, I can control the number of turns in a field winding. Thereby, the flux can be controlled. Flux, or which is nothing but MMF, is the product of N into current flowing through that field winding. So by controlling the number of turns, I can control the flux. And third method is the series parallel connection. So we have our armature. So we have the field winding. Series connection, actually the wind is divided into two parts, and the two parts of the winding are connected in series. The resistance is RSC by 2, and here also it is RSC by 2. This is series connection. And then we have a parallel connection in which the two windings are connected in parallel. So this is the voltage V, RSC by 2, this is RSC by 2. This is the series current ISC. So in this method, the series winding is made into two equal sections and connected in series in one configuration and parallel in another configuration. So if you take the ratio of N series by N parallel, it is equal to 1 by 2. Similarly, if you take the expression for torque, we can also do the same derivation for torque. T series by T parallel equal to 2 by 1. Yeah, we'll go to the next topic, that is armature control method. So this is what we have discussed. So the next topic is armature control method. In this method, the variable resistor is placed in series with the armature circuit. We have the field winding here. This is the armature resistance, variable armature resistance. This is the armature. So voltage V plus minus. This is the shunt field winding RSH, ISH. This is the armature current IA. And this is the speed N. So we know that N is proportional to V minus IA RA by pi. So here RA is a combination of armature resistance plus external resistance. By varying the external resistance, the IR or drop will be varied. Flux is constant.
is the voltage is constant. So IRA drop increases for a given terminal voltage, speed increases. So in this method of speed control, we can get only below rate speeds. So if I draw the plot speed and varying the armature current by A, we can speed below the rate. This is the rate speed. So armature control method. In this method, the speed control resistance is placed in series with the armature circuit. Here only the speed below the rated speed can be obtained. This method is less efficient because we have placed external resistor in the high power circuit. Because generally the armature current is very high when compared to the field current. Whereas in case of earlier methods, we have placed the field circuit. In the field circuit, the current is less, so the losses due to external resistance will be less. Method, the armature resistance control method, is less efficient than the field control.
Okay, we see some. This is what we have discussed. So this is a gate 92 marks question. So all these questions. A DC shunt motor is running at 1200 RPM when excited with 220 volt supply. Neglecting losses and saturation, the speed of the motor when connected to a 175 volt supply is. They have given V is equal to 220 volts. The machine is running at 1200 RPM. That is proportional to n into 5. They are specifying neglecting losses and saturation. Right, n equal to proportional to E by 5. That is proportional to V minus IARA by 5. So neglecting loss, so I can neglect this prop. So that's proportional to V by 5. Proportional to flux is proportional to field IF. Know that the field current for a shunt motor is given by E by terminal voltage by field resistance. Right, so the field current 1 will be terminal voltage 1 by the field resistance. Field current 2 will be terminal voltage by field resistor RF. Right. So I can write and 1 by N2 equal to 1 by V2 into IF2 by IF1. So if I replace here IF2 and IF1, I can write 1 by V2 into IF2 is 2 by RF into IF1 is V1 by RF. Cancel. V2 cancel. 1 V1 cancel. So N1 equal to N2 equal to
1200 RPM. Okay, we'll go to the next question. Give 2002 mark question. 240 volts DC series motor takes 40 amps when giving it rated output at 1500 RPM. Its resistance is 0.3 ohms. The value of the resistance which must be added to obtain rated torque at 1000 RPM is. So they are given the terminal voltage is 240 volts. The armature current IA equal to 40 amps. Speed N is equal to 1500 RPM. And the armature resistance and the series resistance RA plus RSC equal to 0.3 ohms. They're asking us to find out the value of the resistance which must be added to obtain torque at 1000 RPM. The back EMF EB1 is given by V minus IA into RA plus RSC. So V is 240 volts minus armature current IA is 40, RA plus RSC is 0.3. So that's 40 minus 12. That is equal to 228 volts. You know that torque is proportional to flux into IA, where IA is also proportional to IA. So in a series machine, torque is proportional to IA square. So T1 by T2 equal to IA1 by IA2 whole square. So they have specified rated torque. There is no change in the torque. So IA1 equal to IA2 equal to constant. Which means the flux is constant. We know that E is proportional to N phi. So EB1 by EB2 equal to N1 by N2 into phi 1 by phi 2. Since flux is constant, I can write EB2 equal to N2 by N1 into EB1. That is 1000 by 1500 into 228. That is 2 by 3 into 228 equal to 152 volts. Now they are asking us to find out the external resistance which must be added to get this 150 volts. EB can be given as 240 minus the current is same 40. We are adding an external resistance 0.3 plus R, that is equal to 152. If you solve this expression, we'll R is equal to 240 minus 52. 40 minus 152, that is 88. 8 by 40 minus point gives us 1.9. We go to the next question. You can get 2003 2 marks question. A DC series motor driving an electric train faces a constant power load. It is running at rated speed and at rated voltage. Speed has to be brought down to 0.25 per unit. Find the supply voltage that has to be approximately brought down to from 1 per unit. Take this question as a homework. Try to solve this question in the next class, and we'll also cover the remaining topics. The pending topics include the DC generator characteristics. Yeah, that's all we have. After that, we'll see few more problems in the next class. Yeah. Thank you all. See you in the next class. Bye.